So before I begin the proof, I'm just going to point out I sketched out a definition of the mean value theorem. If f is differentiable on AB, then there exists a c in AB such that f of b minus f of a over b minus a is equal to f prime of c. So let's begin the proof. And the first thing I'm going to do is I'm going to define a function h of x, which is just going to be equal to f of x minus g of x. So this implies that since f of 0 is equal to g of 0, f of 0 minus g of 0, which is just equal to h of 0, is also equal to 0. And all I did was just subtract g of 0 on both sides of this equation right here. This also implies the fact that h prime of x, which is equal to f prime of x, minus g prime of x, is also less than or equal to 0. And that's from the same fashion as how we got this top equation right here. So now we want to use our mean value theorem. So we're going to let AB be a subset of the set 0, comma infinity. Then by mean value theorem, there exists, we'll call it x prime, which is an element in AB, inside AB specifically. It won't ever be the element A or the element B, such that 0, which is greater than or equal to h prime of x prime, is equal to h of b minus h of a over b minus a. So we're just going to look at the left and right hand side of this inequality, or not inequality, this equation. So 0 is greater than h of b minus h of a over b minus a. Then 0 is greater than or equal to h of b minus h of a. And then h of a is bigger than or equal to h of b. So the motivation for the subset argument is that we know what our h prime of x graph looks like. It's always negative, right? So looking at our original h of x graph, well, we knew h of 0 is equal to 0. And then we know that the function's always going to be decreasing from that point on. It's going to have some flat points, another flat point, then going on forward. So since we know our function's always decreasing, right, we can pick any point greater than 0. Say we pick this for our a and this for our b. And we know that h of a will always be a bigger number than h of b. Even if we pick elements that are right next to each other, no matter how small they are. Call this a prime, b prime, and we're just gonna call this regular a, regular b. Right next to each other, right? H of a prime. Oh god, my handwriting's so bad. And then h of b prime. You can still see that h of a prime is clearly bigger than h of b prime. So that's basically the motivation for the argument we put out with the subsets. So on the side in the green, I've written 3 key facts, and that's going to be really important for us finishing this proof. So we're going to define a specific subset now. We're going to let a equal 0, and we're going to let b equal x. So h of 0 is greater than or equal to h of x, which implies that 0 is greater than or equal to h of x minus h of 0, which and h of x is equal to f of x minus g of x, h of 0 is equal to 0. So that gives us that g of x is greater than or equal to f of x. And that's the end of the proof. Thank you for watching.